This video is to help review for the final exam in Chemistry 1211. The final exam is the standardized ACS exam, ACS standing for American Chemical Society. It consists of 70 multiple choice questions, so you have about a minute and a half per question because it is 2 hours long. A reference sheet, similar to what you've seen on previous exams, will be provided. The equations for that will not be given to students, is prohibited to copy or give away anything on the exam. So just study the equations as best you can. There is no writing on the exam. Please bring a Scantron and a number 2 pencil. Scantrons, of course, can be purchased at the bookstore. I think they're in packs of 5. I'll have extra number 2 pencils, but not enough for everybody, so just do your best to bring some. Scratch paper will be provided just like normal. It is cumulative, so it does cover all chapters, so you need to remember stuff chapter 1 all the way through the final chapters. And then the study guides to help you study are available in exam resources on Blackboard, and that will focus on some of the topics that may or may not be included. So this is just an additional review with explanations for problems to try to help you understand the problems a little more deeply, especially since it's been a while for some of these types of problems. So how this review is going to go is I have a set of 30-some problems that I'm going to go through one by one, usually just a problem per slide, and explain how to answer them, some tips for figuring out the right answer or at least narrowing it down to give you a better chance of getting them right since they are multiple choice. On the very last slide, or one of the last slides, is the answer key to these problems. So if you encounter a problem that comes easier to you, that you're more knowledgeable about, feel free to fast forward and go to the next one. Or you can just use the PowerPoints provided without the video to go through these on your own. All right, so first off, you're going to need to know the polyatomic ions. This is mainly going to be used in naming on these multiple choice questions. So we memorized the polyatomics at the very beginning of the semester. If you made flashcards, you might want to review those again. So the problem we have here, it gives us lithium chloride as the name and wants us to figure out the formula. So one key to figuring out if a polyatomic is involved by looking at the name is to look at the ending. So in this case, chlorite ends in ITE. Now, most of the time, if it's not a polyatomic, it's going to end in IDE. There are exceptions to this, such as cyanide, for example, but most of the time when it ends in IDE, that's an element from the periodic table, not a polyatomic. Okay, so if you see ITE or ATE, those are strong clues that that's a polyatomic and should be named accordingly. So since we see this ITE, that means I can go ahead and get rid of this LiCl. That's going to be lithium chloride with the IDE ending. So that narrows it down a little bit for me. Now, to figure out the rest, you're going to need to know the naming process, right? So ClO versus ClO2 versus ClO3. So if you remember, ClO is going to be the hyperchlorite. ClO2, that is just chlorite. So C is going to be the correct answer. And then ClO3, that's chlorate with that ATE. So remember, one of the hints to trying to figure out based off of oxygens is that the one with the most oxygens is usually ATE, and then a little less oxygens will be ITE. No solubility tables are given. However, there are some trends that might be easier to remember when encountering a problem about solubility. So as far as the chlorides go, bromine and iodine, they are mostly soluble. The most notable exception is going to be silver chloride, and anytime mercury or lead are involved. Sulfates are mostly soluble, so looking at a polyatomic here, SO4 sulfate. The exception meaning when it's insoluble, are going to be when sulfate is with mercury or lead once again. So you're noticing the trend for insoluble, right? Mercury and lead. And last but not least, potassium ion, sodium ion, ammonium, and acetate, as well as NO3 being the nitrate ion, are always soluble no matter what they're attached to. So other than polyatomic ions, you'll also want to be able to name covalent compounds. So an example for number 2 here, if they give us the chemical formula, for instance, of CO, what is that the formula for? So some things to note here is that both the C and the O are capitalized. Okay, so that means it's 2 different elements combined, not just one element in itself. So that's going to take out copper and cobalt, because if it was copper or cobalt, there would only be one capital letter followed by a lowercase letter. So our next 2 choices then are carbon monoxide and monocarbon monoxide. And if you remember from that chapter when we learned about covalent compounds, is we always take the mono off of the first element if there's only one of them. So this makes C the correct choice. Looking at naming transition metal compounds. So transition metal compounds are one of the harder ones to name. This is where we use the crisscross method after we figured out what the oxidation number is. So the oxidation number is the charge on each of the individual ions. And then we would crisscross those charges to come up with the formula. So here they're giving us the formula, Fe2O3, and we need to pick out the name. So we're doing the reverse crisscross essentially. So to figure out the name of it, this 2 subscript that's on iron is the charge on oxygen, and you can double check that because if you find oxygen on the periodic table, it's in group 16, and most elements in group 16 like to form a -2 charge because they're nonmetals, and they're 2 away from having their full octet. Now we do the same with the subscript on oxygen. So the subscript on oxygen is 3, so that would tell us that the charge on this iron then is going to be 3, but more specifically a +3, because remember, transition metals and metals in general like to form cations, positive charges. So that tells us that it's iron with a 3+ charge. Why is that important? Because if you remember, naming transition metals, we always put Roman numerals after the transition metal indicating what the charge of the transition metal is. That's why 3 of your choices have the Roman numerals right after the metal name. D is obviously an incorrect choice, and this is because of the use of prefixes. So if you remember, we only use prefixes for covalent compounds, and covalent compounds are between 2 nonmetals. In this case, we have a metal with a nonmetal. So coming back to the answer here, we just figured out that it was iron with a 3+ charge, so that means we'll want to pick choice C, iron Roman numeral 3, and then oxygen becomes oxide. We're adding that IDE ending. So C is the correct choice here. So this particular question has to do with a balanced equation. So it's asking why is the equation incorrect? And it gives us a reaction scheme here. Now, it has magnesium with a subscript of 3 reacting with nitrogen with a subscript of 2, forming Mg3N2, or if we wanted to name that compound, little practice here, it would be called magnesium nitride. So let's look at A. First choice is saying some of the subscripts are incorrectly used. Okay, so that means these little subscripts that we just pointed out. That's possible. I think that that could possibly be a choice. So let's look at the other choices. The other choice B says the equation is not balanced. Well, it's clearly balanced if we're looking at making sure that there's the same amount of magnesiums and nitrogens on both sides. And there is, so it's definitely not B. C, the valence of the nitride ion is incorrect. So what they mean by the valence of the nitride ion, so we're looking at the nitride ion, so it would be the nitrogen that's in a compound, because that's when it would form an ion because it's with a metal. So to figure out if the valence of the nitride ion is incorrect, we're looking at the subscript on magnesium, because that's the crisscross method, right? So it's telling us here that magnesium has a -3 valence, a -3 charge. And if you look at the periodic table, yes, it does. So that is incorrect, because based off where nitrogen is in row 15, I shouldn't say row, column 15, it will form a -3 charge. Now the choice D is saying the valence of magnesium is incorrect. So for that, we're looking at the subscript of nitrogen, because we'd have to do the crisscross method to come up with this chemical formula. So that subscript of 2 is going to become the charge or the superscript on magnesium, meaning that magnesium has a +2 charge. And if you look at magnesium, it is an alkaline earth metal in group 2, and it will indeed have a +2 charge. So D, also not correct. Choice E, the coefficient of N2 is incorrect. So coefficient is going to be the number in front. And we already discovered that the equation is balanced, so this cannot be a correct choice either. So I'm going to go ahead and cross that out. So that leaves A as the only possible correct choice. And it is the correct choice. And the reason I know this is because when you look at magnesium, magnesium metal, when it exists by itself, exists with only one atom of magnesium. It doesn't pair up with 2 other magnesium atoms. Okay, the only elements that do that pair up with atoms of the same element to provide more stability are those 7 elements that we talked about in class that make the number 7 on the periodic table, which is hydrogen. Obviously, nitrogen's one of them because it likes to form N2, oxygen, and then those halogens, fluorine, chlorine, bromine, and iodine. Okay, those like to form diatomics. We call those the diatomic ones. Magnesium, a metal, does not pair up with other magnesium atoms to be more stable. It exists by itself, as do most other metals. Okay, so A is going to be the correct answer here. Looking into some questions on the structure of an atom. So question 5 is asking us, in all neutral atoms, there are equal numbers of, so this is where you need to know the structure of an atom, obviously, and then the subatomic particles, electrons, protons, and neutrons. So you remember protons and neutrons are the 2 subatomic elements that live in the nucleus of an atom. Protons are positively charged, making that nucleus positively charged. Neutrons are neutrally charged, no charge at all. And then we have the electrons, which aren't in the nucleus, but are surrounding the nucleus in an electron cloud, orbiting it essentially. Okay, so for a neutral atom, we're looking at the 2 subatomic particles that have charges. And the 2 subatomic particles that have charges are electrons and protons. So those need to be equal in order for the atom to be equal. All the others are incorrect. This last one is trying to trick you, as you can see in choice D, because it says positrons instead of protons. So just be aware of those tricky questions. All right, 2 more on atomic structure. So here's number 6 and 7. You might want a periodic table out to work through these, because you will have a periodic table on the exam to use to help answer the questions. So for number 6 here, the atomic mass of an element is 32.07 U. Okay, so that's the atomic mass units on the periodic table. Its atomic number is 16. The number of protons contained in the nucleus of an atom of this element is, well, this is where your knowledge of protons being the same as the atomic number. Okay, so the number of protons is always the same as the atomic number. If you change the number of protons, you're changing the identity of the element, right? So A is going to be the correct choice here. The atomic number and the protons are the same thing. Now number 7, the atomic mass of an element So it's the same atomic mass as the previous question, the same atomic number. Okay, so this is where the periodic table will probably help you. If you find number 16 on the periodic table, you'll see that it's sulfur, having a mass of approximately 32.07, depending what periodic table you're using. Now, what we know about sulfur is that it's in the same column, the same group as oxygen, and oxygen likes to form what charge when it forms an ion? It likes to form a -2. So sulfur will follow suit. Since it's in the same group, it has similar tendencies and will also like to form a -2 ion because it is 2 away from having its full octet. Number 8, in what respect does an atom of magnesium differ from a magnesium ion? Okay, so we're talking about neutral magnesium. That's what they mean by an atom, when it's neutral versus when it has a charge. Okay, now remember, the reason that metals and nonmetals like to form charges is because they're trying to reach their full octet in the ionic compound. So looking at A, the ion has a more stable electronic arrangement than the atom. Yeah, that's true, but always go through the other choices to make sure, because we just said that atoms like to form a full octet to become more stable, and magnesium forms a +2 because it only has 2 electrons in its valence shell, and once it loses those 2 electrons, then it's isoelectronic with the noble gas in the row above it. So it's more stable that way. Okay, so A is definitely a big possibility. Let's look at the other choices though. B, the positive charge on the nucleus of the ion is 2 units greater than the nuclear charge on the atom. Honestly, I'm not even sure what that means, so we're just going to say no. Going to C, the ion has 2 more protons than the atom. Now this one is all kinds of false, right? If you change the number of protons, you change the identity of the atom. So if the ion had 2 more protons, it would no longer be magnesium. It would now be a completely different atom. Okay, so that one's completely false on all accounts. D, the ion will react more readily with free chlorine. Now this one, you might think, oh yeah, it's got a charge already. It's ready to rock. It just wants to react. No, okay, because it's actually more stable when it has the charge because it's isoelectronic with a noble gas. Okay, so the neutral magnesium will react much, much more readily than magnesium with a +2 charge. You might have even seen cases where people react magnesium with water and it's explosive, fire. Like it's very reactive metal when it's neutral, when it's in its pure form, versus when it's in a compound and has its full octet. So D, incorrect as well. So A is the correct answer here. Next, we're going to look at isotopes. So which of the following represents a pair of isotopes? So if you don't remember what isotopes are, a little reminder here at the bottom. Isotopes are atoms of the same element that have a different number of neutrons. Okay, so the neutrons differ. So it has to be atoms of the same element. That's key here. And their mass numbers, or their number of neutrons, is what differs. Okay, so looking at choice A here. Now looking at their mass numbers, that's these numbers in the upper left-hand corner, their mass numbers are the same. And we just said they have to be different. Also, so are the elements. They're different, but they need to be the same. Okay, so A is definitely wrong. B, elements, they're not the same, so B has to be wrong. C, elements are the same, okay, but now let's look at the mass numbers. Mass numbers, different. So C is going to be the correct answer because they're atoms of the same element, so they're both chlorines, and their mass numbers differ because they have a different number of neutrons. Okay, so obviously D is incorrect as well. Number 10, again with isotopes. So if you were given an isotope symbol, also referred to as a nuclide symbol, and you had to calculate the number of protons, neutrons, and electrons. So here we have cesium with a mass of 137, it looks like, and then it even gave us the atomic number, the number of protons, being 55. Now if it doesn't give you this last number, this number 55, remember you can figure that out by looking up the atomic symbol. So if you find cesium on the periodic table, you'll see that it's number 55 meaning that's the number of protons it has. So sometimes this number is omitted. You can always find it as long as you have the symbol. Okay, so a little reminder on this. Mass number is the protons and neutrons only, because electrons have such a low mass that it's negligible and we don't count it. So that's what we're going to focus on. For the charge part, since it's neutral, so figuring out the electrons, since it's neutral, meaning I see no charge right here, so it has to be neutral, we know how many protons we have and we can figure out the electrons based off of that. Okay, in this case, they're going to have the same since it's neutral. All right, so going to solve for this. Remember, with nuclide symbols, it's really nice that they are set up like this because first off, this number 55 here, that gives us the number of protons. Okay, so that's our protons. So since we know that's our number of protons, we can kick C and D out of the loop here. So to figure out the number of neutrons, we can just put a line underneath these two numbers because the top number, 137, is the mass number, 55 is the number of protons. So when we subtract those two, we get 82. So there'll be 82 neutrons. So that means it's either A or B. Now moving to the electrons. What did we just say about electrons? Well, in this case, since it's neutral, the electrons and the protons have to be the same. They have to equal each other so they can cancel each other out. So A is going to be the correct choice here. All right, next let's look at isoelectronic. So if you remember from when we talked about isoelectronic atoms, they're atoms that have the same electron configuration. It doesn't mean that they're the same atom or even the same type of atom. Okay, just the same electron configuration. So for a question such as this, which pair of particles has the same number of electrons, what I like to do is I take each pair, I figure out what noble gas they're isoelectronic with, and if they're both isoelectronic with the same noble gas, then they're going to have the same number of electrons as each other. Okay, so I'll show you the process. Going through A here, so we have fluorine with a -1 charge. So finding fluorine on the periodic table, if it has a -1 charge, that means it gained 1 electron, so it's going to be isoelectronic with neon. Let's see if magnesium has the same noble gas that it's isoelectronic with. So magnesium has a 2+ charge. So finding magnesium on the periodic table. So if it has a 2+, that means it's losing 2 electrons. Okay, so we're going to go backwards. So losing 1 electron, we would be at sodium. Losing another electron, we're at neon. So both of them are isoelectronic with neon, meaning they will have the same number of electrons as each other. So they'll have the same electron configuration. I'll quickly go through the other 3 choices to show you why they're not correct. So B, neon and argon, those are both noble gases. Obviously, they have different number of electrons. Okay. C, looking at P with a -3 charge. So phosphorus with a -3 charge is going to be isoelectronic with 1, 2, 3, argon. And then aluminum with a 3+ charge. So aluminum right here, since it's a 3+, that means it's losing electrons, so it's going to go backwards. So it's going to be isoelectronic with the noble gas in the row above it, meaning isoelectronic with neon. So they're isoelectronic with different noble gases, so that one's incorrect. Bromine, bromine with a -1 charge is going to be isoelectronic with krypton. And then selenium, neutral selenium, stays where it is, right? So they're definitely going to have different number of electrons. Revisiting bonding briefly. So which of the most complete and best description of a covalent bond? It's kind of an oddly worded question. But that's such as life, right? So looking at A, so remember covalent bonds. What do we know about covalent bonds? We know electrons are being shared. We know they're usually between 2 nonmetals or else a nonmetal and a semi-metal sometimes. That's all I can think of at the moment. So let's look at the choices and see. We're going to go in the backwards order this time, starting with D. So looking at choice D, does this describe a covalent bond? A system of 2 nuclei where each atom donates 1 electron? No. Donating electrons suggests that there's an ion being formed, so D would be incorrect. C, a donor bond in which one atom donates an unshared pair to the other? I mean, no, it would be more sharing, not an unshared pair. That's a tricky answer. Let's look at B. I'm not ready to cross that one off yet. The attractive force between two atoms of opposite charge. Yeah, definitely not. That's describing an ionic bond through and through. Looking at A, a system of two nuclei with a pair of electrons being shared between both nuclei. Well, A is definitely a better sounding choice than C, so A is going to be the correct answer here. Okay, number 13. Which pair of elements is most likely to react to form a covalently bonded species? So for covalent bonds, remember they are either between two nonmetals or between a nonmetal and a semimetal. So you need to be aware of where the metals, semimetals, and nonmetals are on the periodic table. So this one's color-coded. The one you will get is not going to be, okay? So the nonmetals are the ones in green here. The yellow ones are the semimetals. So we're looking for elements that are either yellow or green. And by yellow, I mean this color yellow, not the yellow of the alkaline earth metals over here. All right, so looking at the choices, I think A is the choice right off the bat because we have phosphorus and oxygen, and those are both nonmetals, if I'm not mistaken, right? Phosphorus is right here, oxygen right here. So A is going to be the correct choice. And if you look at the other options, they all have either alkaline earth metal for calcium, alkali metal for potassium, and then zinc is a transition metal. So those are definitely ionics. So here's another bonding question. This one's asking which chloride should exhibit the most covalent type of bond. So all of these compounds have chlorine in them. So that's what they mean by chloride. And the most covalent type. Okay, so that doesn't mean it's going to be our classic two nonmetals or a nonmetal and a semimetal. Okay, so what's going to help you here is knowing the trend about electronegativity on the periodic table. So what I mean by that is the trend for electronegativity is that it increases as you go up a group and increases as you go across. And the periodic table that I have up here actually has the electronegativities of all the elements present. You're not going to have one like this, but I'm just trying to show the answer is correct as we go through. So how are you going to do this one without the actual electronegativities? Well, first off, find where chlorine is, right? So chlorine is very close to this upper corner. So chlorine is very electronegative. So what is going to make the most covalent type of bond is another atom that is almost as electronegative as chlorine. Because if they're sharing electrons, the closer their electronegativities are to each other, the more covalent that bond is going to be, the more equal that sharing is going to be, the closer their electronegativities are. Because if they have similar electronegativities, that means they want the electrons similarly, and they're going to be more likely to share, if that makes sense. So what do you need to find to go with chlorine? Well, whichever one of these choices is closest to this corner is going to be the correct choice. So let's look. We have sodium. So I'm just going to circle all of them. We have sodium, we have potassium, we have calcium, we have barium way down here. Definitely not barium, right? That's very non-electronegative in this bottom corner. And then we have beryllium. So out of all of these, beryllium is the one that is highest up in a group, and it's also the one that's furthest to the right, meaning it's got to be the most electronegative one. And the values on this table confirm that. So beryllium chloride, choice E, is going to be the correct answer because since their electronegativities are the most similar, they'll be most likely to share those electrons. Right, so here's another bonding question. And to point out this bottom table that I have here, the nonpolar, covalent, polar, covalent, and ionic bond, this part would not be given to you on the exam. So I pulled this out of one of the PowerPoints just as a reminder for like what section we talked about this in, try to like trigger some of those latent chemistry memories that you have. chemistry knowledge. All right, so number 15, the compound of which two elements is most likely to involve covalent bonding. So very similar as before, right? But this time, what they're giving you is the electronegativities of each of those elements. So the correct answer is going to be whichever two have the closest electronegativity, the closest to each other, so the least difference. All right, so let's look at the choices. We have Q and Z. So Q and Z, yeah, that's definitely not the correct choice. Those are the furthest away from each other, so that would definitely be an ionic, so not A. Next, let's look at R and T. So R and T, they're not too bad. They're relatively close to each other, so maybe. Now, choice C, we have T and X. So T and X, oh, T and X are much closer. Look at that difference, 2.8 and 3.0. I want to say T and X is going to be the winner, but I want to double check those last two choices just in case. R and X, no. R and Z, definitely not. So C is definitely your choice. Correct answer because of the very small difference between those two elements. So the next two questions are based off chemical equilibrium. This is not a topic we discussed during lecture. However, in my research at looking up what type of practice problems and study things for the ACS, chemical equilibrium was a topic, and there was some practice problems I saw. So I wanted to cover it briefly. So with chemical equilibrium, it's really just a reaction scheme in which we have not a double-sided arrow, but an arrow pointing one direction on top and an arrow pointing the other direction on bottom. So this chemical equilibrium is showing that there's an equilibrium between reactants and products. It means that products are forming just as quickly as reactants are forming. Okay, so both are existing in equilibrium rather than there being more products or there being more reactants. Okay, so that's all there is to it. So when we're looking through these choices, we have choice A. The frequencies of reactant and product collisions are identical. No, there's no way to tell that. B, the concentrations of products and reactants are identical. No, it's not about concentrations. The velocities of product and reactant molecules are identical. That's chemical equilibrium, has nothing to do with speed. D, reactant molecules are forming products as fast as product molecules are forming reactants. So D is the correct choice here. It's saying they're in equilibrium. It's going the same rate in both directions. And then E, the number of moles of reactants and products are equal. No, it's not about the moles being equal. It's not about the concentrations being equal. It's just about the forward and reverse reactions are going at the same speed. So here's another equilibrium question asked in a slightly different way. Maybe give it a try on your own based off what I said. You can feel free to pause. So chemical equilibrium is the result of A, a decrease in speed of reaction. No, it has to do with them being the same in the forward and reverse. B, the unavailability, of one of the reactants. No. Stoppage of further reaction, definitely not, because that's reactions continuously going in the forward and reverse direction. D, opposing reactions attaining equal speeds. Yes, D is going to be the correct choice. And then we have E, formation of products equal in mass to the reactants. No. So next we're going to look at some calculations, in particular the mass percent calculation. So a question might look something like this. 18. What is the mass percent of oxygen in calcium nitrate? So if we were naming that formula, it would be calcium nitrate, so that's something you should know as well. So in this case, they're talking about just oxygen. So the equation that you would need to use is the equation below. I'm not sure if this is given to you or not. I'm going to assume that it's not. So to figure out the percent of a specific element, you're taking the number of atoms of that element, which you use the subscripts to figure out, multiply it by the molecular weight of that element, which you can find on the periodic table. In this case, oxygen's molecular weight is 16. And then last but not least, you need to divide by the molecular weight of the compound as a whole. So you're going to have to calculate the molecular weight of calcium nitrate, which could be another type of question on its own, calculating molecular weights of compounds. Last but not least, you multiply by 100%. So let's look and see how we're going to do this. All right, first off, the number of element atoms. So we're talking about oxygen here. So we see oxygen has a subscript of 3, but notice it's part of a polyatomic and it's inside of parentheses. So there isn't just 3 oxygens, there's actually 6. And I know this because of this 2 on the outside of the parentheses. That 2 is saying there are 2 NO3s. So if there are 2 NO3s, that gives us a total of 6 oxygens because we would multiply the subscript on the outside of the parentheses by the subscript inside. So 3 times 2 gives us a value of 6. Now the molecular weight of the element itself you find on the periodic table, which we said was 16 grams per mole, and then you divide by the molecular weight of the compound as a whole. So to calculate the molecular weight of a compound, you need to make a list of each element present, and then you take the number of atoms of each element that are present in that chemical formula, and you multiply it by the molecular weight of each of those elements, and you find that on the periodic table. So since writing with the mouse does not turn out too well, I'm not going to go through the entire process here, but I just wanted to show you the setup. So once you calculate the molecular weight of calcium nitrate, you would put that in the denominator here, and I'll let you do that on your own, but I'll still give you the answer. So you'll take 6 times 16 divided by the molecular weight that you get of the entire compound and all its parts, including the calcium, the nitrogen, and the oxygen. And once you do that, the answer that you should get is B. 58.5% of calcium nitrate is made up of oxygen. Next, we're going to look at a conversion calculation actually, between grams, moles, or atoms. So if you remember, whenever we're going between grams and moles, the piece of information that we need is molecular weight. So you're either going to be dividing by molecular weight or multiplying, depending upon which direction you're going. When you're going between moles and atoms, you want to use Avogadro's number. So you're either going to multiply or divide by Avogadro's number to go between moles and atoms. Once again, depends what direction you're going. So in this case, the question asks if we have a 24-gram sample of carbon, how many atoms does that contain? Okay, so you would need to start with the amount given to you in the question, which is 24 grams. And you can't go directly from grams to atoms, as you can see from the scheme above. You have to go to moles first. So in this case, when we go to moles, we're going to be dividing by the molecular weight because we want the gram portion on the bottom. So the molecular weight of what? Of carbon. So the molecular weight of carbon is 12 approximately. It's actually 12.001, but I don't want to try to write all those numbers. So 12 grams per mole. This allows the grams and grams to cancel, and if you stopped here, you would be left with moles. But the question wants you to go all the way to atoms. So once you're here, your next step then is to use Avogadro's number. So in the case of Avogadro's number, we're going to multiply by Avogadro's number. So it's going to go on the top here because when you look at the units on Avogadro's number, in this case, the units are going to be atoms per mole. Because remember, it's entities per mole, so sometimes the word is atoms, like in this case, because they're using the word atoms. Sometimes it's molecules. Sometimes it's photons. I mean, we've used it for plenty of different things. So 10 times to the 23rd atoms. I'm just going to write AT because this is getting a little bit ridiculous. And then the mole portion goes on the bottom. Okay, so you can see that's canceling. The grams are, the moles are, oops, and then we're going to be left with just atoms. So in this case, once you do that calculation, the answer you should get should be answer C. Now make sure you try these in your calculator. You don't know how many times I've seen people do the correct work and
have calculator issues because they aren't sure how to use it, and then get the wrong answer. So let's move on to the next. So I went a little out of order here and back to balancing equations. So in a balancing equation problem, it's kind of nice when you have multiple choice actually, because if you're not very good or confident in your ability to balance an equation, you can just take the possible choices and then plug them in as the coefficients and figure out which one gives you the same atom count on both sides of the equation. Okay, so in this case, with the iron, what is that, iron 3 oxide added to carbon monoxide. So we need to figure out which of these is going to have the same amount of irons, oxygens, and carbons on both sides of the equation. So you can make the list and start doing the atom count, or like I said, if you're not feeling that, you can just plug in the numbers. So for instance, if we were to plug in letter A, and I'm going to focus on just the carbons here, because if you'll notice, carbon is only in one spot on the reactant side and on the product side. So if I can balance out my carbons, everything else should follow suit. So for the carbons, it looks like for choice A, we got a 1 in front of the first carbon and a 12 in front of the second. That's not going to work for us because that means we'll have 1 carbon on the reactant side and then 12 on the product side. So that's definitely not the answer. Moving to choice B, we have 1 carbon on the reactant side, 6 carbons on the product side. That's also not going to work, right? They have to be equal to each other. So we need the second number and the fourth number to be the same. That's going to give us the right choice. So C, also not correct because we got a 2 and a 7. So I'm going to cross that one out. Last but not least, oh, here we go. D has a 1 and a 1 for the carbon spots. So that one should be the correct answer. Plug it in and double check that the irons and oxygen also match once you find the right answer. Next, we're going to look at a stoichiometry problem. So here they gave us a balanced chemical equation because, as you know, for stoichiometry, the first step is having a balanced chemical equation because you use that in order to move between moles of one reactant or product to moles of a different reactant or product. So this question is asking, in the following reaction, how many moles of water are needed to produce 4 moles of calcium hydroxide? Okay, so calcium hydroxide, looking at the reaction scheme, the coefficient in front of it right now is a 1. Okay, so in order to do this problem, we need to first look at what two we're comparing. So we already know it's calcium chloride. The other one is water. So I'm just going to underline those two so that we make sure we're focusing on that. So in order to do stoichiometry with these, we need the mole ratio. So that's why you need the balanced chemical equation. The mole ratio is the coefficients in front of each one. So the mole ratio that we have between water and calcium chloride is that 2 moles of water will produce 1 mole of calcium hydroxide. Okay, well, the question is asking, well, what if you wanted to produce 4 moles of calcium hydroxide instead? Well, in that case, we would need, if we wanted 4 moles here, that means we would have to multiply by 4, right? To go from 1 mole to 4 moles, we'd multiply by 4. So we want to do the same thing to the water. The moles it currently has, we want to multiply by 4 so that we get 4 times the amount of the calcium hydroxide that we want. So that means we are going to need 8 moles of water. So C is going to be your correct choice here. Some people as well like to just do a straight up mole ratio calculation with the railroad tracks. So 4 moles of calcium hydroxide is what we want. We're going to use the mole ratio, putting the moles that represent the calcium hydroxide, the 1, on the bottom because we need that to cancel out because this 4 moles is representing calcium hydroxide as well. And then the 1 representing water is the 2 mole part, right? So that would go on the top because we're figuring out how many moles of water are needed. That way, moles of calcium hydroxide both cancel, leaving us with moles of water, and it gives us the same answer as the previous way I did it, an answer of 8. So for electron configuration, you need your periodic table most likely. So what is the electron configuration of silicon? So for that, you need to know where the s, p, and d orbitals are, and we read the periodic table just like a map. So the s is this first container here. So we want to get all the way to silicon. So you need to find silicon on the periodic table. It looks like it's number 14 here. So when we're done, all of these superscripts should equal up to 14 because the superscripts represent the number of electrons. So looks like to get there we need to start at hydrogen, so we go through the 1s2 and then we hit period 2, we get 2s2 and we want to keep going. We hit the 2p's, we go all the way through giving us 2p6. Then we hit period 3. 3s2 gets us to magnesium. Then we hit the 3p's. 3p what? Well, silicon is the second one in the 3p block, so it would be 3p2. So the correct answer here is going to be choice C, because that gives us exactly what we need. It looks like they tripped us up a little bit by trying to add in these 3Ds here in the other choices, so just be aware of that. You don't hit the 3Ds until you get into period 4, because the Ds are one less than the period they're in, so just be careful of that. Next, we're going to look at molecular geometry. So I've seen several questions while I was looking up practice problems for the standardized exam, and then I also saw a few on the Blackboard review that is posted talking about the hybridization of a lot of these orbitals in molecular geometry. So I wanted to touch upon that because it's really a small layer to add on to, and I really would like you to have the opportunity to get these questions correct if you do see them on the exam, because I have a feeling you will, since I've seen a lot of these in my research here. So number 23, it's saying the ammonium ion is symmetrical. So if you remember the ammonium ion, ammonium being NH4 polyatomic, it is nitrogen at the center, it's even telling you, and it's a tetrahedron, so meaning it's tetrahedral in shape with 4 equivalent hydrogens. So the bonding of this ion can best be described how? Okay, so they're talking about the bonding around the nitrogen atom itself. So nitrogen's the central atom, and they're saying what type of hybridization is going to be around that guy. So to explain this, hopefully briefly, I have this little table off to the side here. So first off, whenever we're talking about these molecular geometry compounds, most of the time it's going to be the hybrids, not any of this pure P or pure S bonding. Okay, so for the hybrids, what do they mean? Well, this is how you can relate them to what we already know. Okay, so when we talked about molecular geometry, we talked about how many things are around the central atom. And if you remember, things could either be an atom they were attached to, so it doesn't matter if it was a single, double, or triple bond, it's just how many atoms total that it's attached to, as well as electron pairs that the central atom has around it. So either atoms or electron pairs can be counted as things, right? So for sp, that means 2 things, because we're using 1 s orbital and we're using 1 p orbital. So 1 plus 1, 2 things. What are the possible molecular shapes for 2 things? Only linear. Now sp2, this is going to be for 3 things, because we're using 1 s orbital and 2 p's for a total of 3. Okay, and remember, those things can be atoms or they can be electron pairs. So if all of those things are atoms, it's going to be trigonal planar. If all of those things are, if 2 of those things are atoms and 1 of those things is an electron pair, then it's going to change the shape and it's going to be bent. It'll still be sp2. Both of those shapes apply since there are 3 things around the central atom. Lastly, we have sp3, so as you can guess, that's going to be when 4 things are around the central atom. So if all of those things are atoms, like in the case in this problem, it's tetrahedral. So that's our specific case here. So we know that our answer is going to be A, sp3, because there are 4 things around the central atom. Now, if one of those things is not an atom, but an electron pair instead, that's where we're going to get the pyramidal or trigonal pyramidal, as we called it in class. And then if two of those things are electron pairs and the other two are atoms, it's going to be linear. So based off of what you just learned about the sp hybridization and how it relates to molecular geometry, see if you can answer this question. Which geometry is associated with an sp hybridized atom? So remember, sp hybridized means there are only two things around it. Okay, so if there are only two things around it, the only possible choice is going to be linear. How do you know it's two things? Because there's one s orbital and one p orbital for a total of two. I'm going to throw another one in there. So here we have an sp hybridized central atom can be used to describe which one of the following. All right, so sp, what did sp mean? How many things could be around the central atom? Two. Okay, so let's look at choice A. How many are around the central atom in choice A? 4, so that's not right. That's going to be sp3 hybridized. Let's look at B. So choice B, it does have two things. Okay, so carbon is central, because remember hydrogen can't be central. That means it just has hydrogen and nitrogen around it. Okay, so this is a possible choice, but we don't know if there's lone pairs on it because we haven't done the structure, because lone pairs count as things too, so we don't want to pick that quite yet. Moving into choice C, there's 2 hydrogens and 1 carbon for a total of 3 things, so that guy's out. Last but not least, we got D, OF2, so this is a possibility as well, right? We have oxygen with 2 atoms around it. But just because there's 2 atoms around it doesn't mean that there isn't lone pairs on the central atom. And in this case, once you draw out the structures of B and D, so you count the valence electrons in C, B is going to be the correct choice because carbon will have a triple bond to nitrogen and a single bond to hydrogen, causing it to have that sp hybridization because it only has 2 things around it and no lone pairs on the central atom. When you look at the OF2, it's going to be very similar to H2O, water. Oh, and then I start drawing water as I say that, sorry. So what that means is it's going to have 2 lone pairs on the oxygen for a total of 4 things around it, because 2 lone pairs plus 2 atoms. Now you might even see a problem that deals with dipole moments. So if you remember, dipole moments are when a compound is polar. Okay, so they give you the chemical formula, but they also give you the shapes, and the shapes is what's really going to help you here. Okay, so if we look at the carbon dioxide, it says it's linear. Well, if you have a linear carbon dioxide, that means you have a carbon with 2 oxygens on either side, and the dipole moments are going to cancel each other out. Okay, and if you draw this, you'll see that carbon has a double bond to both of the oxygens, meaning there are no lone pairs on the central atom and all terminal atoms are the same, so non-polar for carbon dioxide. Sulfur dioxide, this one's bent. I want to go ahead and say this one's probably our answer, because if it's bent, that means those oxygens aren't canceling each other out, and there's going to be a dipole moment. So far this is my choice, but I want to check the rest of the answers just in case. Looking at choice C, BF3, trigonal planar. So boron was one of the exceptions to the octet rule where it was happy with just 6 electrons. So if we have boron in the center with 3 fluorines around it in a trigonal planar manner, what that means, if it's trigonal planar, is that it does not have any lone pairs on the central atom. So if there are no lone pairs on the central atom and all the terminal atoms are the same, this guy is also nonpolar, meaning no dipole moment. Last but not least, we have CF4, and this is tetrahedral. So once again, central atom, no lone pairs on it, and all terminal atoms are the same, so that's nonpolar as well. So choice B is going to be our answer. Let's look at some redox reactions. So for redox, we learned some mnemonic devices that could help. One of them was oil rig, and then the other was Leo. I think it was Leo the lion says grr, or something like that. So oil rig stands for, oil is losing electrons, reduction is gaining electrons, and then Leo the lion says grr is losing electrons is oxidation, gaining electrons is reduction. So that's how we're going to remember the difference between oxidation and reduction. So it gives us actually it looks like a balanced half reaction, redox reaction, and they're asking which one is true for the reaction. So let's look at A. Fe3 plus is oxidized. Well, let's look. It's going from a 3 plus to a 2 plus. So if the charge, the plus charge is going down, that means it gained an electron because electrons are negative. So if it gained a negatively charged electron, it's going to become less positive. So if it gained an electron, that means that Fe3 plus was not oxidized because gaining is reduction. So A is not the choice. Now how about B? Fe3 plus increases in oxidation number. Well, its oxidation number is originally 3 plus, but then it goes down to 2 plus. So it does not increase, it actually decreases. So that's incorrect. Fe3 plus is reduced. We already said that. It definitely is. So that's going to be the correct answer. Double checking this last one though. I minus is reduced. Let's see. Iodine went from a -1 to its diatomic form, which makes it neutral. That's how it exists in nature. So if it went from a -1 to 0, that means it lost an electron. Losing electrons is oxidation. So yes, that one is indeed incorrect. In the chemical reaction, we have solid zinc and copper 2 sulfate, making zinc 2 sulfate and solid copper. So let's look at the choices. Metallic zinc, so that's going to be the one that's a solid, that's not an ion, is the reducing agent. So remember, reducing agent is the one that is oxidized. So let's see, is zinc oxidized? Well, it went from zinc neutral to zinc with a +2. And losing electrons, which is what happened here because it went from a 0 to a +2, so it lost 2 negatives to become positive. Losing electrons is oxidation. So if losing electrons is oxidation, then A is correct. Zinc is the reducing agent because the reducing agent is the one that's oxidized. Looking at gases, which is something that we just tested on for number 29 here, it's asking in which gas are the forces between molecules strongest? Okay, so these are the intermolecular forces. So we need to use our knowledge of intermolecular forces, so London dispersion versus dipole-dipole, hydrogen bonding, or even all the way up to the ionic. So let's see here. Looking at the first choice, neon, well, neon's a noble gas all by itself. All it's going to have is London dispersion forces. Okay, so definitely not strong. Remember, London dispersion forces are the weakest out of all of them. So I know it's not going to be neon. CH4. CH4 we said does not have a dipole moment. It's nonpolar. All hydrocarbons are nonpolar. So the only thing that's going to have is London dispersion, so that's not it either. Looking at choice C, O2. O2 is symmetrical, it's not polar. All it should have is London dispersion forces, and then we get to water. Well, water is a polar molecule, so you initially think dipole-dipole, but it actually has hydrogen bonding because of the OH. So due to its H bonding, D is going to have the strongest. Now, if the choices had choice E, for instance, and it was an ionic compound, the ionic compound would have the strongest forces. Just so you know that any ionic compound could be sodium chloride, could be calcium carbonate, anything. Okay, so that would change the answer. Just want you to be aware of that. So looking at gas calculations, obviously you'll probably end up having some calculations either using the ideal gas law, that PV is equal to nRT, or even using the combined gas law. But this one is relating to STP, so standard temperature and pressure. Remember, standard pressure is 1 atm and standard temperature is 273.15. So this is asking, what if you had 2 moles of any gas at STP? Well, if you remember, 1 mole was going to be 22.4. That was that standard number. So if we had 2 moles, we would need double that. So D is the answer here. So here is a gases calculation where you need to use one of the equations rather than just your knowledge of what STP means and the molar volume that occurs at STP. So for number 31, they're talking about a sample of helium gas, a 1200 milliliter sample at a pressure of 350 millimeters of mercury and a temperature of 300 K. Now they're saying, what would be the volume of the gas sample if the pressure changes, increasing, and the temperature changes, increasing? So notice we have 2 volumes, 2 temperatures, and 2 pressures. So we're going to need the combined gas equation, which is the P1V1 over T1 is equal to P2V2 over T2. Okay, and they're asking us to solve for volume, so that needs to be rearranged to solve for V2. So you can see the rearrangement and how that is done below. Okay, so now all you need to do is figure out what the values of each of those are and then plug them in. So the nice thing about equations such as this is that the pressure, for instance, we see that it's in millimeters of mercury. We also see that the volume is in milliliters. We don't have to change that. Okay, when we use the ideal gas law, the one that's PV is equal to nRT, when there's only one pressure, one volume, one temperature, okay, then we have to have the volume in liters. We have to have the temperature in Kelvin. And the reason for this is because of that constant, that R value, because that R value has the units of liters, of ATM, of Kelvin, okay? But for the equation below, we can keep it in whatever units it's already in, other than temperature. Temperature always has to be in Kelvin, because whatever units it's in, that's the units that are going to come out. So what I mean by that is, since they gave us volume in milliliters, when we solve for volume for V2, the answer is going to be in milliliters. Okay, so now you just need to plug in. I like to make a list of knowns and on the side so that I can plug it in with ease. Do whatever works for you. Once you plug all of those values in, I believe the answer is going to be, sorry, I had to do a quick calculation. It's going to be B, 800 milliliters. Last question I'm going to go over is one that I saw on a review that I found online. Which instrument is used to measure the gain or loss of heat? Now this one we should know because we've done it in lab. So it's actually a calorimeter. So just wanted to end on an easy one here. Whether or not that will be on the exam, I'm not sure. But all right, so we're going to end with some rules and tips. As far as the exam goes, first off, you need a Scantron, so make sure you purchase that from the bookstore. They come in packs of like 3, 4, something like that. You also need a number 2 pencil. No writing on the exam, 70 questions, which gives you about 1.5 minutes per question. So if you don't know it at all, guess and move on, okay? Because you don't want to be stuck. And if there's one that you're not sure about, write it on your scratch paper what number it was and continue on. Just make sure that you skip that one on your bubble sheet. Last but not least, practice topics you've had difficulties with. So if I've been reviewing some of these topics and you're like, oh, redox, I have forgot about that completely, make sure you're looking at it. Okay, you also want to Make sure you're reviewing more topics than I covered in this review, because this review had, what, 30 questions, and you have 70. There's going to be a lot more topics than I've covered. I've just tried to cover the ones that I've seen most prevalent in the reviews that I've looked up. So you'll want to know the reaction types, so like combustion reaction versus single displacement reaction versus decomp or synthesis. So make sure you're looking at stuff like that. I recommend that you go through the reviews that I made for each of our exams, and not necessarily the homework assignments unless you want extra practice, but the reviews, okay, because that'll be less problems. The reviews are designed to help you with types of questions you'll see on the exams, which are going to be less intense than the types of questions you've seen on the homeworks. So that's why the reviews are a good one to look at. And then it gives the cumulative topics of that those particular chapters, which will help you focus on which topics you've had difficulty with, so you can focus on those topics more. And here are the answers for all of the problems that I went over during this review. Let me know if you see any discrepancies or errors so that I can change it and let other people know. Thank you.